Hello everyone, I'm Yatin, and today we will continue our discussion on efficient LLM inference or efficient LLM decoding that we started yesterday. So till now we saw that why are we talking about efficient inference? That's mainly because of the inefficiencies in the inference. For each token we have to run forward pass. For each token we have to run a forward pass, right? Whereas in training we could process all the tokens parallelly, right? So this is obviously slow, and as a first thing we saw that we can avoid some redundant computations, right, by caching whatever we compute in the previous iterations. So we created a KV cache, but then we saw that the way KV cache is created and the memory is allocated on the GPU, that is very inefficient, primarily because we need contiguous memory. And then we saw VLLM and paged attention that efficiently manages the KV cache and uses paged attention to compute attention over the the KV blocks that it creates, right? So we looked at avoiding recomputation and efficient memory management. Now, can we do anything else? Can we speed up the attention computation itself, right? And you have already covered, I think, flash attention that actually looks at speeding up the computation of attention, right, at the time for training. So let's first quickly revisit what flash attention does, and then we will see how we can apply that at the time of decoding, right? So just to recap, the memory in our system follows this hierarchy where this is the GPU memory. So for example, when you have an A180 GB, that 80 GB is the memory that you talk about, is essentially HBM, right? However, when you have to do any computation, we load tensors from HBM to SRAM and perform any computation that is to be done. But here it's very fast, but its size is restricted, right? So when we look at the implementation of attention, a naive implementation of attention, right, it requires 3 or 4 operations, right? Each operation is, let's say, a single line in PyTorch, but if you abstract that, those are abstraction of certain things, right? For example, matrix multiplication. Actually, when matrix multiplication is happening, those tensors are being moved from HBM to SRAM, and then all the computation is happening, right? And then we have to write it back for other operation, for example, masking, right? Once we have done masking, we have to write the tensor again back to SRAM for doing softmax, right? So this requires multiple read and write back and forth from HBM to SRAM, right? And this is the bottleneck in flash attention. That is the core idea, that because you are naively using some abstract operations from PyTorch, let's say, to compute softmax, which involves 3 independent abstract computations, right? This makes it slow. So each operation, for example, here is called a kernel, right? You have a kernel for matrix multiplication, you have a kernel for masking, a kernel for softmax, right? So the core idea of flash attention is that instead of using these operations, how about writing a fused kernel which will copy it once to SRAM, do all the computation, and write it back. So that is the high level idea of flash attention, right? Which is essentially an IO aware implementation. And how does it happen? So essentially they use a standard technique called tiling. We discussed that yesterday as well in context of paged attention, right? It's about computing the softmax over a bigger computing the softmax over, let's say, n vectors, right? You compute it over smaller vectors and then combine them, right? So you want to compute softmax with over A1, A2. You first compute softmax over A1 and A2 and then combine, right? And so yeah, we covered this yesterday. And so this is an animation from the flash attention blog. In their implementation, what they do is that they parallelize things with respect to query and batch size, right? So for each query, right, each query will be run parallelly. For each query, they will compute the softmax, right, using the fused kernel implementation in parallel, right? But now when we are decoding, consider the scenario, for example, where there is only one query, there is only one request, right? And now these days these models support context length of up to 32,000, right? And let's say I'm doing content grounded question answering. The content itself is huge. There are a lot of keys and values, but there is only a single query at any iteration, right? So essentially we need to modify this, because here, right, we are using fused kernel, but parallelization happens across multiple queries at the time of training, right? But now if we have a single query and we have multiple key value pairs, how should we go about it, right? So the trick is very simple. What they do is that they split the keys and values into, let's say, different blocks, right? Here they have created 5 blocks, right? They use standard flash attention to compute softmax over each split. So here, right, standard flash attention is being applied, right? So we have this query, right? We are loading a set of KVs, doing some computation and reducing it there, right? This is happening in one process, and in parallel we have 5 processes. We can compute softmax parallelly in those 5 processes over different set of queries and different set of keys and values for the same query. And we know that the softmax is distributional in nature. We can then combine them as well, right, by maintaining the sum of numerator and denominator separately, right, in the softmax, right? So this is the basic idea, which is very similar to what happens in flash attention for training. The only difference is that their parallelization happens across queries, and here, to introduce parallelism, we split the entire sequence, the entire prompt, very huge prompt that we have, into smaller splits, and for each split we use flash attention to compute the attention over that split only, and then we combine as we usually do using tiling. So this is the comparison of flash decoding with respect to other methods, right? So this is flash decoding, and on the y-axis you have tokens per second, the throughput. How many tokens are you able to generate per second? Even with respect to flash attention v2, right? This is much better, right? Because even in flash attention v2, we are not taking the advantage of splitting the input prompt into different chunks, right? So for a query, it will still happen serially, right? Okay, and with respect to standard PyTorch, using standard PyTorch primitives, this is the throughput that we get in blue curves, yeah, right? So it gives us up to 8x speedups in decoding when we are decoding for very large sequences primarily, right? Okay, so till now, again, we first looked at KV caching, paged attention, which is efficient management of the memory, right, of GPU memory, and then we looked at flash decoding, which is efficient attention for very, very long sequences with a single query. But still, generation is sequential, right? Even now we are generating one token in one iteration, right? This again makes it slow, because if you're generating only one token in each iteration, it still remains memory bound. Most of the processors are empty because they are because of that, right? We cannot do anything about it as well, right? So how can we break this, right? How can we break the sequentiality in the generation? What we're talking about here is that for a single prompt, I don't need multiple samples right now. I am interested primarily in a single sample, but instead of generating it one token at a time, I want to generate multiple tokens at different time steps. In beam search, you generate multiple tokens at the same time step, right? Here we don't want that. We want multiple tokens at different time steps. So let me give you a hint. Let us suppose that I am able to guess. We will talk about how do I guess. Okay. Let's say the input prompt is the cat sat, our standard prompt, and I make a guess. The cat sat on the chair. Now, can I use this guess somehow? So what we do here is that we first make a guess for the input prompt, right? For example, we have on the chair. Remember that at the time of training, we are able to process the entire sequence in one go. I can forward this entire sequence in one go and get all the probability distributions, right? So this is the input prompt, and I have the probability distribution here, which is the distribution for the next token, right? And then here again we have the distribution over the next token, this is the distribution, right, from which we would have sampled provided the previous token is on, right? Okay, so now let's focus on this distribution right now. Let's say this comes out to be the token with the maximum probability here, right? This happens to be the token with the maximum probability. We compare it with what we had in our guess, right? This, let's say on has the highest probability and we have on, bingo, there is a match, right? So we accept that, right? Now let's say here probability of A is maximum conditioned on this sequence, the cat sat on, right? But what we have here is it doesn't match, right? So we can't accept that, right? So what we have done, we have been able to generate only one token on, right? Okay, should we stop here or can we do anything else? We have only gotten a single token on, right? Is that it, or do we have anything else? So why are we rejecting right? So we get two tokens, on and right? We reject the guess, but we replace it with the token selected by the model, which is essentially A. It's even if our one guess is correct, we are good. And even, okay, so in one forward pass, we are able to generate two tokens, right? Okay. So what we are doing essentially here is that we make a guess, we check whether you want to accept this or not, this accepted, accept this or not, rejected. And once we can't, this is to answer your question, that we can't use rest of the completion as it was dependent on the token that has been rejected by the model, right? And the new input prompt with which we run the next iteration would be the cat sat on, and we have this as well. So this is our new prompt and we'll make a new guess. Let's say now the new guess is the cat sat on a chair. Instead of that, we have a cat sat on a table, right? And we will run the forward pass again, and this time we have to focus on this distribution, right? It says mat. Our even first guess is wrong, right? But still it doesn't go wasted, right? Because we get mat, right? So we replace this table with mat. So even if our guess is not correct, even if a single guess is not correct, we have a lower bound of 1. So it will be at least as good as standard inference. We'll at least get one token. Okay, so this is what speculative decoding is. We guess, the input prompt is the cat sat, we make a guess on the chair, we verify, we accepted one token, we rejected the chair, but still, we can replace this with the token that we get from the model, which is so the new prompt for us will be the cat sat on With the new prompt, we will make a new guess again and then repeat the process, right? Now, so we will cover that, right? We will come to how do we sample, but let's now answer the question, how are we guessing, right? What is the right way of guessing? Because that is a bigger piece here. All of this discussion was, under the assumption that we have a good guess. So what we do essentially is that, okay, let's motivate. Why would that work? But let me motivate that, right? So let's say the question is a group of flamingos is called, and we have a 100 billion model which has to answer this question, right? The next token is A. I mean, this is easy. And the next token is a little difficult. Does anyone know here what is a group of flamingos called? Okay, I also didn't know. It's called flamboyance, right? So, right, this is difficult. This is easy, right? You can predict A easily. Anyone can do that, but this is difficult. So, do I really need a 100 billion model for predicting this A? Probably not, right? I can maybe use a 1 billion model to create a small draft in some sense, right? So let's say I pass this through a small model, let's say a 1 billion model, and it generates an answer of flock. Of course, this is wrong, but at least this token is correct, right? So I can use this here and then correct flock, right? So, right, we will accept this token we will reject flock, but then we will have a distribution over flamboyance, and we will be able to accept that while we are verifying, right? So this is an example from staged speculative decoding paper. Here you can see that only the red tokens are the one which are generated by the bigger model. Rest everything was generated by a smaller model was able to guess that. I mean, this is essentially following a syntax, right? And if a small model knows the syntax of the coding, it should be able to generate white spaces at least, right? Right. So it's similar to generating an article in the previous sentence, right? So this is exactly what we do in speculative sampling. And if you're doing greedy decoding, as we saw earlier, it was easy. But then there was a very pertinent question that if you're doing sampling, then how do we go about it, right? What is the right way of doing it? Okay, so anyone knows how do we do that? Let me abstract out the problem here, right? What we have essentially is that there is a draft model, which is MP, and then there is a target model, which is MQ, right? Let's say we are on a particular token, the cat sat, right? The distribution that I get from the token sat, which is for the next token, right? Let's say that token, that probability is P, right? I have a distribution P because when I'm running the forward pass, I will have the distribution over all the tokens conditioned on whatever tokens that I had earlier. I have this distribution P, right? And when I am running the forward pass, we saw that when we are verifying, we had the distribution Q as well, right? Even when we are verifying, we get the entire distribution conditioned on the previous input. So we have Q of X as well, conditioned on x1 to xt minus 1, right? We have drawn a sample x tilde from here, right? Now, is this a good sample from Q or not? That's what we want to judge, right? So have you studied something similar to that earlier? If you cannot sample from a difficult distribution like Q, but you already have a sample from an easy to sample distribution P, then how do you go about it? How do you generate samples from Q? Very much similar to that. Yes, that is very close, right? Importance sampling is actually indeed what it is, right? So the technical term there is called rejection sampling, right? That is the concept there. So let's quickly look at the setup here. So PF is the prefix that corresponds to our x1 to xt minus 1 that we have. Let us say we want to generate 5 next tokens, right? So we get first sample x1 from MP, which was the draft model, right? We get x2 up to x5, right? But in addition to these tokens, we also have the probability distributions P1 till P5, right? Conditioned on, of course, they are conditioned on the previous tokens that we have, right? Now, when we run the target model to verify, remember that we again get the distribution at each step, right? So this Q1x is the distribution for the first token, Q2x is the distribution over the second token, and so on and so forth, right? So these are distributions at every step and distribution over all the tokens. Okay, so here as an example, let's say the completion is dogs love chasing after cars. This is the completion after the input prefix. And what we have shown here is the probability of these tokens only, dog love chasing after cars, right? In actuality, we have the distribution over all the tokens, right? At each step, even at step 1, we have distribution over all the tokens, right? And let's say these are the probabilities that we get from the target model. Okay, and now I have to decide whether I should accept this dogs or should I reject this, right? So this is exactly similar to rejection sampling, where we have already sampled something from a distribution P, and I want to decide whether I will get the same sample indeed if I sample from Q, right? So the algorithm is pretty simple. It simply says that if essentially you have to accept the proposal with probability Qx over Px, right? So we say accept X with this probability, right? And how do we do that? So let's say in this case, this comes out to be, let's compute that. In this case, it comes out to be 0.9 by 0.8, this is greater than 1, right? We have to accept this with probability greater than 1, so we will definitely accept that, right? Here it comes out to be again probability 0.8 by 0.7 greater than 1, so we accept this, right? Now here it turns out that we have to accept it with the probability 0.8 by 0.9 roughly. Let's say this is 0.9, right? So essentially we have to accept this with the probability 0.9. What we do is that we sample a uniform from a uniform distribution between 0 and 1. If the number comes out to be less than 0.9, we accept it, right? So that is exactly what is rejection sampling is. So if qx is greater than px, then we accept, and if qx is less than px, then we accept with the probability qx by px, right? Qx is the target model and px is the draft model, right? Does this make sense intuitively, right? I mean, if a small model has already accepted this, has generated the sample with when its probability was 0.8, and the target model is assigning a higher probability than that, then intuitively it makes sense to accept that, right? But now what happens if you reject? Let's say you accept this, you accept this as well, but you reject this after, right? So now what should you do, right? So earlier we had the distribution over x4. We do have the distribution right now as well over x4. We can sample from there, right? But instead, I will not go into the proof of this, but what they propose is that instead of sampling from qx, don't sample from qx directly. In this case it was q4 of x, right? Was it? Yeah, q4 of x. Don't sample from there, but sample from qx minus px plus. So what is qx minus px plus? So let's say again, just to illustrate that, let's say these are all the tokens that we have, and this is the probability distribution. This is the distribution using the draft model, right? And this is the distribution using the target model, right? So here what we are saying is that, okay, for this is the case where we have rejected a particular sample and we want to get something else in place of it, right? So it says that first of all, for the cases when qx is less than px, right? So here q is less than p, right? You don't sample from here. You focus only on these tokens only, right? Where q is greater than p, right? I mean, intuitively, here anyway the probability of q is low. It's lower than p, so we are ignoring that space. And when only for those tokens where probability of the target model is higher than the probability of the draft model, right? That's where we focus, and essentially we compute the difference q minus p here. This is the gap. This is q minus p, length of this vertical line, and we sample these tokens with probability proportional to that, right? So we normalize it and then sample, right? So this is essentially rejection sampling, and this answers your question: how do we do when we have to do sampling instead of greedy decoding? And incidentally, this technique was proposed simultaneously by a group of researchers in DeepMind and Google research, right? Okay, so this is an illustration, how much speed up do we get, right? So this illustration is from the Google paper where they focus on an encoder decoder model, right? T5, and this time is taken for encoding. You're encoding using a T5 model. This is standard time, and this 1 unit of time here is for decoding one token at a time, right? So this is the wall time, right? When you generate one token, the wall time moves ahead, right? So this is the total time that you will need to generate these many tokens. And now if I have k equal to 3, right, I generate 3 tokens from a draft model, and then 1 token from the bigger target model, right? So essentially there are 3 bands here, 3 blue. These are 3 tokens which are generated from the draft model and that takes very less amount of time, right? After that, 1 token is generated by the bigger model, so that takes a lot of time, right? And so on and so forth. So you can see that there is a huge reduction in the wall time, and if you use k equal to 7, it further reduces, right? So these results are from the DeepMind paper, I guess, and on different data sets they also show up to 2x speed up. So this is This is autoregressive sampling, standard nucleus sampling, and this is speculative decoding, right? Okay, so we looked at one method of guessing, right? Which is in speculative decoding, we have a smaller draft model which we are using, and we are using that to make a guess. But do we always have that, right? Do we have? I mean, of course, if we have a smaller model from the same family, we can use that. We can use a 7 billion model for a 70 billion model, right? Right? But is 7 billion small enough? So, I mean, there was again a tweet which said that Meta should have released a couple of 1 billion models as well, because 7 billion is not good enough, so that it can be used as a draft model, right? And there could be some issues with hosting two models in the same system. So, can we do something else about it, right? So that is the hypothesis here, that the smaller model is not going to be slow. I mean, if it is slow, then less weights, less memory, and we are working in a setup where memory is the bottleneck, right? So by definition, it's not going to be slow. It's essentially a transformer-based model, right? I mean, the same operations you are doing, and you have less number of parameters. That means less memory and more efficiency. Once we have a big model, let's say we have a 100 billion model, right? We studied about something called PEFT in our last few lectures, right? We looked at parameter efficient fine tuning, right? So can we combine these two things? Instead of retraining the entire model from scratch, what I do is that I train multiple language model heads. So we have this one language model head, right? So we have this embedding E that we get, right? And we have a matrix M which maps this E to a distribution over all the tokens in the vocabulary, right? Token 1 till token V, right? This is called a language model head, this M, right? Now what we are proposing is that, create more such heads. These are simple linear layers, a single, with one hidden layer maybe, right? And their task is to generate the next token, not the next token, but next token, right? And this fine tuning is simple. This is not difficult, right? Because you can do PEFT. You can have all of this can be trained using PEFT, right? And if you have access to the training corpus, right, earlier, then you can use that to run these. You can use that to train these heads, and it won't take. I mean, yeah, they say that it doesn't take more than 5 to 6 hours, depending on the size of the data set, right? So we train multiple heads after freezing the backbone. So this is frozen, right? So we are not compromising on the quality of the base model. We are just training, attaching multiple heads on top of it, right? Okay, we create these multiple heads, and then when we run the inference, let's say we are running inference at some iteration, each head can give us some top k tokens, right? Let's say we have k equal to 3, right? So we can pick top k tokens from each of the heads, right? Or we can sample these 3, whatever. Using these top 3 tokens from different heads, right? I can generate multiple possible potential completions, right? So one could be it is difficult not. The other could be it the difficult, right? I is right? So I can take a Cartesian product here to get all potential completions. Some of them will not make sense, of course, right? So that's what we do next. We take a Cartesian product to create all the potential completions, and it will give us certain candidates, right? So let's say these are the candidates that we have, and now our job is to verify these candidates, right? Earlier we were verifying only a single candidate, but now we have multiple candidates that we need to verify, right? How will we do that? How will we verify multiple candidates if we have to do that in one forward pass? Is it possible? Does anyone know? Okay, so for that they use something called tree attention. I'll quickly cover this, right? This will enable you to parallelly in one iteration verify all the candidates and select the best, right? So essentially you will get some sort of a score for each of the possible completions, and then you have to have some acceptance criteria there, right? So they devise an acceptance criteria which essentially makes sure that you get the largest subsequence which passes certain test, right? We'll look at that as well, right? So the first step here is training multiple LM heads. This is easy, right? We can do that using PEFT. We saw that, and yeah, and here we figure out when they trained multiple heads for Vicuna 7 billion, they figure out that the top one accuracy is approximately 60%, right? Which is very low, right? Because if you are creating a path here, right, 60%, 60%, 60%, 60%, that will be 60% times to the power 4. That will be very low, right? But then top 5 accuracy is 80%. So it makes sense to evaluate multiple completions instead of just going for one greedy completion, which anyway will have a very low probability of acceptance, right? So therefore, this gives them the idea of keeping top k predictions from each of the heads and create a Cartesian product. Okay. Then this is simple. This we discussed, that you create potential completions using the Cartesian product, right? And then we process all the candidates in parallel, which is enabled by tree attention. Let's quickly look at how tree attention works, right? So the idea here is that let's say this is a simplistic example where let's say first head gives you only 2 tokens. We select only 2 tokens from first head, it I, and from the second head we select 3 tokens, is apostrophe the, right? So how many possible completions are there? 2 times 3, 6, right? It is it apostrophe it the, and similarly with I is I this and I the. So this is essentially a tree that we are creating, right? Now if I have to process only this, let's say I create an attention mask like this here, right? So these 2 are for both the tokens, right? And then these are replicated 2 times. So this so essentially we have 8 tokens here, right? And if I have to look at a particular path in the tree, which is let's say it followed by is, right? It will depend on itself, right? It will attend to itself. And when I have this token, let's say this represent the path it is, right? This token is representing it is, right? This is has to attend only on it. It should not attend on I, right? So we create an attention mask where we don't attend on this, but we attend on this, right? So the mistake that I did earlier was that I was looking at the transpose, right? These are the queries, and these are the keys, right? So this is that path here, and when I am computing the attention for is, I have to attend on is and I have to attend on it, right? And I don't have to attend here, right? So this will be 0, right? Similarly, when I am here, this path is I is, right? This node represent I is. So here I will have an attention mask for this particular query, right? Which all keys will it attend on itself and on I, right? Is this making sense or is there a confusion? I can go over it again. Okay, so let's go over it again. Right, so let's say from the first head we accept 2 tokens, it and I. From the head 2 we accept 3 tokens, is, apostrophe and the. Total combinations are 6, right? And to parallelly process all of this in one go, they devise something called tree attention, right? They creatively modify the attention mask, right? So what they do, for example, is that let's say I'm looking at this particular completion, it is, right? So for this token is here, right? This token is has to attend on itself, and it has to attend on it. It doesn't have to attend on I, right? Whereas if I look at this completion I is here, it will attend on itself, is will attend on itself and attend on I, right? It will not attend on anything else. So we can appropriately add position embeddings as well and create an attention mask, right? And basically each node here, each node, all of the 8 nodes that we have here gives us a potential subsequence, right? Whenever we get the probability distribution at this step 8, right? This is essentially a potential completion as well, right? There are not only 6 but 8 completion. It is also a potential completion. I is also a potential completion. It is also a potential completion, and it apostrophe and it the, right? And similarly with I. So we have total 8 potential completions here. That's why we have 8 cross 8 attention matrix here. And at each point, by modifying the attention matrix, the mask, we are ensuring that a token is attending appropriately, to the appropriate token in the past, right? So this is what they use, tree attention mask. And yeah, so okay, so we saw earlier that if we take the Cartesian product, it's going to be a huge number of options, right? So the total number of new tokens that we will have to add are going to be total number of nodes in the tree, right? And how many nodes are there in the tree? 2 to the power k, which is a lot, right? Not 2 to the power k, but 4 to the power k, whatever, depending on the branching factor, right? So what they do is that they create a technique to prune the tree. They do not consider all the potential completions. What they do is that they remember that we saw that their accuracy at top 1 was 60% and accuracy at top 5 was 80%, right? So essentially they know that what is the accuracy at each step, right? So for a potential completion, they can compute the accuracy, right? So for example, if I have 8 is, right, I know what is the accuracy here and I know what is the accuracy at the second step. Multiplying the two will give me the potential accuracy for that subsequence, right? So I can use that to statically prune the tree a priori, right? So this is the tree that they are showing, and red is the greedy one, right? And these are the nodes in the tree that they are considering, that they obtain after pruning, right? They do not consider, for example, the subtree here that is there, right? Okay, so again, so they show that pruning the tree helps. If you randomly select a dense subtree, you will always have a budget of how many subsequences you want to verify in parallel, right? So what you can do is that either you can randomly select a connected subtree with those many nodes, or you can prune the tree. And this is what they're showing, that if you randomly subselect, depending on the budgets that you have, number of candidate tokens that you want to, or candidate subsequences that you want to evaluate, this pruned attention tree gives us a better accuracy, acceleration rate, right? Okay, so fine. So this brings us to the last part, where we have to decide how to accept a particular candidate sequence, right? So maybe we can quickly go through it. We will not go into the detail. I'll just give you a high level intuition. So instead of using standard, they don't support standard nucleus sampling. They devise their own sampling method, right? They devise their own acceptance criteria. And intuitively, the idea is that you select a token, right, a candidate, based on 2 things. One, what is the probability, first of all, that is given by the model to that, of course, right? Your selection should be proportional to the probability assigned by the model for that token. And second is the entropy at that particular point, right? So for example, let's say the entropy is low. What does that mean? What does that mean if the entropy over all the tokens is low at a particular point? How would the distribution look like? Less random, yeah, peaky, right? So if it is peaky, if the entropy is low, then I should have a higher bar of accepting a particular token, right? And if entropy is high, That means, there are multiple tokens over which the probability is distributed, a good amount of probability mass is distributed, and therefore I can adjust my threshold accordingly, right? So for each token, they have a dynamic threshold, whether to accept that proposal or not, right? And that threshold is determined by two things. One is a hyperparameter that they have, and this is entropy, right? It's a function of entropy, right? And if this threshold is high, entropy is low, right? Okay, so, and we select the longest subsequence in which all tokens satisfy this criteria. We don't have to select the entire sequence, right? We can select a subsequence as well, right? We might have generated 4 tokens, but only out of that 3 are good, right? For those 3 for which this criteria is satisfied. Okay, so this essentially demonstrates the impact of this threshold. If you increase the threshold here, the selection criteria, you are becoming more and more rigid. So your the accuracy, the acceleration rate reduces, right? This here, but your performance score increases. I mean, yeah, this is a crude linear approximation to these curves. Okay, so this is expected, and this is what they show. They get roughly 2x speed up in terms of tokens per second that they are able to generate, and this brings us to another way of guessing. Right now, what we have looked at speculative decoding, where we used a small draft model with the same tokenizer to make the guess. Then we looked at Medusa, where we trained additional language model heads, right, to create some candidates and candidate n-grams, and they use tree attention to creatively evaluate all the candidate n-grams simultaneously, right, and then accept or reject based on a threshold. Now, can we do something else? And this brings us to whatever points that you raised earlier, right? If we can find from the prompt, if we can find the prefix in the corpus, can we use that? And you defined that thought that we can index the entire corpus and retrieve, right? So that is called retrieval aware generation, which we will discuss in the next lecture. And even if you're doing, so that's broadly is called content grounded QA, right? You have some content and you have to do QA on top of those content, right? Or summarization. You already have information and you have to summarize that, right? In such scenarios, this is a very good strategy, right? So this is called prompt lookup decoding, right? So let me just play this video which demonstrates that. This is taken from the authors directly. Right, so this is the current prompt that we have, right? They take French tribe. This is the prefix that they're taking from the current prompt, and they're looking it up in the corpus or in the retrieved content, or essentially the prompt that they have. Whatever prompt that they have, they are searching within the prompt. That prompt may consist of retrieved documents. That prompt may consist of whatever you're summarizing, as in this case, right? So this gives us the search for it, and it gives us some candidate tokens, right? So here the candidate tokens are this striker, whatever this is, right? And then you pass it through the language model to verify, right? So you generate candidate tokens, and then you pass it to the model to select, and you accept these tokens from the draft, and you get one new token, as you saw earlier, right? You always get one new token from the last step, right? And then you keep on repeating this, right? So this is what we discussed, and right, and this video is essentially demonstrating the kind of speed up that you get, right? So this is done. This is using prompt lookup decoding, and this is still going on, right? And all the colored tokens are essentially the ones they were able to search in the prompt. Only few tokens were generated by the language model. Okay, so this is the speed up that they get, roughly 2.4x, right? So we have looked at speculative decoding, where we use a small model to make a guess. Medusa, where we train multiple heads. We looked at prompt lookup decoding, where we use the prompt to search for a guess, right? Now, can we, again, the next thing is that, can we create potential candidates without using the input prompt? without training separate language model heads and without using a smaller model, right? So I think we are going to skip that. That is called lookahead decoding. I can broadly talk about it. The idea is it's another fancy way of generating n-gram candidates, and then you verify them using, whatever we saw in Medusa, using tree attention. We do not have to train any additional language model head here, and it doesn't even rely on the input prompts. Broadly, the idea is that you start with a random sequence, right? So you have, let's say, an input prompt, and you randomly select x1, x2, x3, x4, and x5. This is a random selection, right? But intuitively, we know that the language model given x2 will select a good next token, right? The bigrams will make sense, right? The cat sat on, after on, most likely an article is going to come. Is going to come, right? Even if this happens to be on, this token is, let's say, on randomly, whatever token that we will get at this step, right? We will have a distribution. When we are verifying, we will have a distribution here. This distribution will be heavily dependent on this token itself, on, right? And it most likely it will select here, right? So even if we start with a random sequence, a forward pass will give us some bigrams that those are potentially, those can be potentially used in the future iteration, right? So even if you start with random tokens here, the token which the language model will suggest here, the token which, let's say, has the maximum probability here, let's say so we get on it's a candidate bigram that we can evaluate, right? And then if it is a good bigram, then I can have this prefix, and right, when in the next iteration, let's say I'm verifying this diagram on right? Now I know that this is a good bigram. When I get a distribution at this place this will be a distribution over the next tokens, right? And most likely it will be a good trigram now, right? On let's say table, on a table is a good trigram potential candidate, right? Right? So intuitively it is starting from a random sequence, doing in the verification step, it gets the next tokens, which gives it a bigram, right? It has multiple bigrams now that it has to verify, for example, right? It will verify it using tree attention that we saw earlier, and in the process it will give trigrams, right? And if we repeat the process, we can maintain a cache of multiple n-grams and validate them simultaneously in parallel, right? So there are two parts in the lookahead decoding. One is creating this candidate, and the second is verifying those candidates, and those can be done simultaneously as well, because we saw that when we were verifying this prefix on this verification gave us the trigram as well, right? So yeah, they do that in one iteration. Okay, so yes, I think we will stop here for lookahead decoding, and if you need more details, you can check out their blog. I will just summarize what we have looked at in these couple of lectures. We first started with the motivation, that why are we talking about efficient inference, right? Because in training we saw that we can process a sequence in one go in parallel, right? But to generate the same sequence, we have to call forward pass multiple times, one token at a time, right? One forward pass for each token. This was not feasible. This was very slow. And as a first step, we looked at KV caching, which was a way of addressing the memory issue, right? Right, and redundant computation. We were avoiding redundant computation when we maintained KV cache, but then the way KV cache was managed, right, in the memory, that was creating issues. And we looked at paged attention in VLLM, which kind of created a novel way of managing the cache in the GPU. And then we looked at flash decoding, which was a variant of flash attention, right? The difference was that in flash decoding, we were parallelizing across KV blocks instead of parallelizing across queries and batch size. We split the entire prompt, which is very long, let's say, into different splits, let's say 5 splits. Each of the split will be processed parallelly using flash attention, right? And then we combine them. We can combine them because attention is, distributed in nature. And then we tried to break the sequential generation process to speed up the generation. There we looked at speculative decoding, which is essentially a guess and verify paradigm. And in order to look at different candidates, different ways of guessing, we looked at a smaller draft model with same tokenizer. We looked at Medusa, and we briefly talked about lookahead decoding, which I have missed. Lookahead decoding, right? So these are the things that we covered, and as a bonus, there is other things as well that we need to take care of when we are creating, when we are using LLM as a server, as a service, right? So when we are using, when we are hosting these language models, for example, VLLM, right? It's or TGI. These are two libraries which are used to serve large language models. Now, in a server setup, for example, consider ChatGPT, right? Multiple users are using it. They're getting multiple requests simultaneously, right? And typically, you process these requests in a batch. You don't process one request at a time, right? And now imagine that if you create a batch, there are going to be certain sequences, let's say this S3, which will finish early. It ends. Now what do you do? Do you continue processing that batch even though you are wasting some resources because this is not done? You are not using the resources there, right? So to handle such inefficiencies, there is something called continuous batching. The idea here is that as soon as a sequence ends, S3 ends here, we fill in it with S5, right? This is the next sequence that we get, request 5. Of course, we will have to pause in between because we have to go through the pre-fill step. Remember that when we get an input prompt, we first pass it the entire prompt parallelly. That is called the pre-fill step, and then we sequentially generate each token at a time. We may have to pause it for a time, for some time, right, to get the pre-fills of S5 and then continue, right? So this is what it shows, that if it ends, we start with request number 5. When this ends, we start with request number 6, and when this ends, we start with request number 7, right? So this is called continuous batching, and yeah, you should check out Orca, which is essentially a framework which implements this. So this is the link for Orca. You can check this out. Okay. So yeah, that's it. And in the end, I think I would like to give credit for the content here, because I might have skipped this earlier in individual slides, but most of the content is driven from the resources that I have mentioned here. Thank you.